gentlemen, I am extremely pleased to welcome you tonight and to thank you for coming tonight. I am pleased for all kinds of reasons, and one of the reasons is that I was in Brookings, South Dakota last night when a blizzard came in, and it did not look good for my arrival here. In fact, we were pretty late getting out, but here I am, and I am not staying overnight in Sioux Falls. Woo! So that means more to me than it does to, well, there wouldn't be anything to anybody else really, but I'm very happy to be here. It is April 1st. I am the official university fool. I usually have some kind of activity to do. All that we did today, which was very brilliant, I wasn't really a part of that, but in our planning that, but the folks I work with in the course put up the most recent exam grades, and they reversed them, so we had a terrible preponderance of F's and D's, and it was, both the two of the perpetrators are right here where I can see them, and they delivered it with deep melancholy of, oh, what could have happened here, and the students were all muttering and worried, and then it turned out it was an April Fool's joke. So, and they don't have cardiovascular problems, you know, the students, so if you get them all agitated, it's not a problem for them because they just have a pretty good heartbeat there. It wouldn't be good to do that to some people of my age, that would not be good, but it was fine to them. So, okay, welcome to FrackingSENSE. Tonight we're going to hear one of the world's experts on the actual process of hydraulic fracturing, Norman Warpinski. And I must begin by saying as well, though, that this event is made possible by a grant from the National Science Foundation Sustainability Research Network for a project on hydraulic fracturing and natural gas development. And I also must note at this point that the NSF does not endorse and is not burdened with responsibility for anything said in this series. We are grateful as well to our co-sponsors for the FrackingSENSE series, the Boulder County government. This is our second to the last FrackingSENSE 2.0 talk, and on April 15th, a sacred day in American life. I always thought it would work better if when you paid your taxes, if you went down to the courthouse and you turned your taxes in person at the county building or something, and dear little squirrel children came dancing out and thanked you for paying your taxes, and it just be, well, that's not going to happen, I guess, because we actually have another more important thing to do. We'll have Josh Joswick here, a former La Plata County Commissioner and a figure now in the Oil and Gas Accountability Project, and quite an interesting person. As usual, it is our priority at these events to make sure that everyone who came can hear the speaker. And so, for the now for the usual FrackingSENSE request, you are free to disagree with the speaker. You're encouraged to disagree with the speaker if that's the direction you want to go. You may note your difference of opinion by sighing with exasperation or snorting with skepticism or even hissing with bitter disapproval, but you must stay within the boundaries of respiratory protest so that you do not disrupt your neighbor's ability to hear the speaker. And we will stick as well with our drill of having you write your questions on the little sheets in the program, or you can raise your hand and get more of those little sheets. Folks from the Southern American West, within 15 or 20 minutes of the start of the talk, will be walking around collecting your questions and also distributing more little sheets of paper if you need them. As to why we stick with that drill, regulars know that I'm intoxicated with the fact that we can get our speakers to respond to a vast number of questions in contrast to the limited number of questions we can cover if we go for spoken questions. Our speaker tonight, Norman Warpinski, received his MS and PhD in mechanical engineering from the University of Illinois. He worked from 1997 to 2005 as a senior scientist at Sandia National Laboratories on projects in oil and gas, geothermal, carbon sequestration, and waste repositories. Now, as a Halliburton Fellow at Pinnacle in Houston, Texas, Dr. Warpinski works on the development of new tools and analyses for hydraulic fracturing mapping, reservoir monitoring, and hydraulic fracturing design and analysis. When I heard, when I heard Dr. Warpinski speak last summer, I felt very strongly that I had found the expert I had been searching for. From a multiplicity of conversations and discussions and rack sessions and exchanges of ideas about hydraulic fracturing, I had finally landed in the company of a person who studies the actual process. What happens in material and actual terms beneath the surface of the earth when fracturing fluid is injected at high pressure into gas or oil-bearing shale. I felt that I was finally in the company of someone who could help me step aside from all of the debates and disagreements involving hydraulic fracturing and help me to get a grasp on what the process means in literally down-to-earth practice leaving me better equipped to return a notch or two smarter to the world of debates and disagreements, the world to which I will return in an hour and a half or so. So I should say as well that Dr. Warpinski has been very generous with his time, coming in a day early to have an intensive day of sharing his knowledge with faculty and graduate students on campus and a number of those who are working in our NSF project. So Dr. Norman Warpinski speaking on hydraulic fracturing, where does the research lead us? Thank you.
Well, that's a great introduction. Thank you very much. A little more background about myself. I've been working on hydraulic fracturing for 37 years. When I started at Sandia National Labs, it was on hydraulic fracturing. I worked there mostly on fracturing, a little bit on these other things that Patty mentioned. When I left Sandia, it was to go work on fracture diagnostics, where we try to map out fractures and figure out where they go. So most of my career has been associated with what do they do, how do they behave, what do they look like. And what I'm going to try to do is try to give you an overview of where the research has led us. And I'm kind of lucky. My career kind of parallels where we've really done a lot of research on hydraulic fracturing. And that's probably not obvious to most people. Everyone thinks this is something new. It's some big black box. We have no idea what's going on. In fact, this all started, and I'll show you a timeline in a couple minutes, with the Arab oil embargo and the gas lines. And the government actually got involved and started doing all kinds of funding of research in hydraulic fracturing. And that's kind of where I'll start and kind of go from there. So I think everyone knows this, right? Hydraulic fracturing is incredibly important for the oil and gas industry. It's about a 40 billion industry. There's several 100,000 that are fracture stages that are conducted each year. In 2013, probably 250,000 or 300,000, something on that order. 70% of the natural gas we use comes from unconventional reservoirs, and there's kind of a plot of it. And basically all of the unconventionals require hydraulic fracturing. So the shale gas right in through here, and the tight gas in through here, and even some of the coal bed methane requires hydraulic fracturing. So it is an incredibly important part of what we need in terms of developing the resources that we use in this country. Not even for export or anything, just what we use in this country. That's probably well known to everybody. So what about the science? The real question I want to talk about is, what do we know about fracturing? What does the science tell us? It's been around for a long time. I think everyone now knows that it started in the late 40s. And everyone thinks, well, okay, so what? We've really not done the scale of fracturing that we do now until just recently. Well, that's not really true. It really started doing what we call massive hydraulic fractures in the 1970s. And because they didn't work out quite as well as we were hoping, that's when all the research funding started going into it, to try and figure out what is happening with these massive hydraulic fractures. And I say massive, and I'll show you a slide in a minute, that these are about the same size as the fracture treatments we do nowadays. Now, they were done in vertical wells, and there were fewer of them in each well, but basically the same size fractures. And so there was a lot of research models, laboratory field data to try and get some idea of what's happening. But going through all this, we came up with the idea, well, we really didn't know enough about fracturing unless we had some way to measure things. And that's kind of where I'm going to go as we move along. We're trying to understand how fractures behave, what they're doing, into, okay, how do we go ahead and measure hydraulic fractures and really understand what's happening. So here's kind of a timeline. And across the top is a timeline of some of the things that happened. So the first fractures were in the late 1940s, obviously. It was the Arab embargo of gas lines, as I said, in the early 1970s that really kind of got this started. We started doing this massive hydraulic fracture in the mid-70s. As I said, it didn't work out quite well. We talk about the Barnett Shales, where that was the beginning of the shales. The first Barnett well was 1981. It took a long time to actually figure it out, but that's when the first well was drilled. We started building sophisticated fracture models. Probably most people don't know. We have a lot of models to figure out how fractures are supposed to behave. We started doing a lot of tight gas sand development in the mid-1990s. The Barnett water fracks, which really started the work in the Barnett, was in the late 1990s. And then the horizontal wells in the early 2000s, which when you marry the horizontal wells with the water fracks, that's when the shale resources really took off. Marcellus in kind of the about 2007 kind of time frame, and then it's going on from there. But let me put a second timeline along here and just throw up a couple of, well, maybe I won't throw up a couple of symbols. There they are. So this is some of the research. It's a timeline of some of the things that are going on. Actually, the research into trying to extract more gas started with the Atomic Energy Commission doing nuclear stimulation. They actually tried to see if they could stimulate a lot of the reservoirs in the West by setting off nuclear weapons, 20, 30 kiloton kinds of weapons, to see if they could fracture the rock up and produce the gas. And that didn't work very well. And that's when they moved to the massive hydraulic fracturing. And obviously there were other problems with trying to do nuclear stimulation. But in many ways it did not work very well. At any rate, they got involved, and this is kind of interesting, what was called the Eastern Gas Shales program. They were actually trying to figure out how to get gas out of the Devonian shales in the eastern United States. Very similar to what's happening in the shales now. They started doing this way back in the mid-70s. We started working on western gas sands. So all the tight gas sands that we have in the Piceance Basin here in Colorado, or in the Uinta Basin in Utah, or the Green River Basin in Wyoming, that's the tight gas sands program. Lots of research on that. And then mine back tests, I'll show you some of those, actually going into mines, creating fractures, mining it back to see, well, what do these things look like? How do they behave? Actually, a lot of information. And a lot of this was funded by AEC first, ERDA second, and eventually that became the Department of Energy. So a lot of it under government funding. So if I start in the middle, we're starting maybe in the 1970s, fracturing started in the 40s. We tried because of peak oil, because of the Arab oil embargo, the doom and gloom years of Jimmy Carter. We really needed to do something else. And so hydraulic fracturing, which had been used for some time, we had developed some very simple models. We really needed to figure out how to do something that would extract more gas. And this is a cartoon that was taken from a paper that was published in 1980. And this is a plan view trying to show that you have these sand lenses, and there's a whole bunch of them. And in a side view, you can see at various depths you have all these lenses. How are we going to get the gas out of these? Let's put in huge fractures that contact lots of these reservoirs and extract gas. And that was the idea. And actually that didn't work very well, as I said. And so we needed to figure out, okay, what's going on? How do we understand what's happening? And just to give you an idea of the size, as I mentioned, I pulled out 4 papers that talked about massive hydraulic fracturing circa 1980. One was by Mobil, one by Columbia Gas, one by Emeco out here in the Wattenberg, and one Exxon actually mentioned a whole bunch of tests, some of them here in Colorado. And if you look at these volumes, which are the things that are in green, they're all somewhere on the order of 3, 4, 6, 8, 10,000 barrels. And that's about the size of the fracture treatments that are being done today. So what's being done today is really no different than we started doing in the 1970s. This is probably about the most you would ever see then. In a vertical well, we might do 6 stages, maybe 8 stages at the very most, but really not very many. On a horizontal well, of course, we'll do a lot more different fracture treatments than maybe 15 or 20 in many cases. But these were done all over the West. The Columbia gas test here was in the Devonian shales, but there's the Piceance Basin, so those are all in Colorado. Uinta's in the Utah. The Boulder was also in Colorado, in the Piceance Basin as well. My clicker's a little slow, or I'm a little incompetent with using it. There we go. So I just wanted to take one step back here and just mention the nuclear weapons, because it's something to think about in terms of what was tried to actually break up and fracture these rocks to try and extract gas. So I put in a picture here that was taken from the report on the Rio Blanco test. 3 30-kiloton devices. So we're talking about a huge amount of energy that's put into these rocks at a depth of about 6,000 feet was the top device. For reference, 30 kilotons would be about 100,000 gigajoules of energy. And if we look at the largest hydraulic fractures that are done today, probably if we pumped at 100 barrels a minute at 10,000 psi for 3 hours, we might get to 200 gigajoules. So we're putting in much more, they put in much more energy into these nuclear weapons. And obviously they did not fracture to the surface, and we obviously don't want nuclear weapons being set off in these reservoirs, but at least gives you a perspective on the amount of energy that's being put into it and what you might accomplish with fracturing versus something like an explosive event like this. At any rate, a lot of the initial work had to do with modeling. We wanted to understand how fractures behave to try to model them. What do they really look like? And actually they started with looking at analogs like volcanic dikes and clastic dikes. Here's a picture, I hope you can see it. It's a great picture of shiprock. And there's this beautiful volcanic dike that comes out of the volcanic neck at Shiprock near Farmington in the Four Corners area. And you can kind of see this dike coming out like this. And this basically looks like a hydraulic fracture. It's obviously formed by lava. And it's created this long fracture, and we looked at these, and okay, these look fairly planar, and let's do the modeling and try and assume that fractures are going to be planar and try to understand how they might behave. And you do mass balance and conservation momentum and all those kinds of things, the standard kinds of processes to try and to put those models together. But of course, what was missing there was the geologic complexity. And we all know that the geology is going to change all of this. The complexity is something that's really going to give us a very different perspective of what's going on if we understand that. So this picture up here is just one of those early, this is from 1961 actually, when they started doing this modeling. Perkins and Kernitz, a very famous paper of some of their pictures of how this looks and what they try to do in terms of the modeling. Actually, it looks very similar to what we do today. So moving into the mine to try and understand what goes on, the Department of Energy actually funded a whole series of experiments at the Nevada test site, where hydraulic fractures are created and then actually mined back so you actually look at fractures and understand how they behave. This is a schematic of one of the mine back drifts. This one's Rainier Mesa. It was called G-Tunnel. We got these mines, these shafts or adits that go way back into the mesa. We would drill wells from the top of the mesa down to the tunnel level, create a fracture, and then mine it back and see what that thing looked like. Other cases, we'd actually do it totally in-tunnel, make fractures with little in-tunnel pumps and then mine it back and see what it looked like, and do explosive tests and all kinds of other tests to see what was the best way to fracture this rock, to control the fracturing, and then try to understand what's happening and what are the geology parameters that are really controlling what goes on. Here's a picture of what one of those fractures look like. This is it's a kind of single fracture up here. It breaks up into 3 or 4 fractures, and there's a lot of complexity you see in these fractures. It's not just this, it doesn't look like that dive I showed you. It actually looks a lot more complicated than that. And this one actually has sand in it, different colors of sand. We put different stages of sand at different colors to try and understand where does the proppant go that holds these fractures open after we stop pumping, and then try to figure out, okay, how do we try to use this information? And these weren't the only mine backs. There were some done in coals, and I'm not going to get into the coals because the coals are even a more complex type of rock, and there's a lot of very interesting things seen in the coals. But a lot of work on the research about hydraulic fractures and how they behave. So here's just a couple more pictures just to illustrate some of the things we would see. This one's looking at a horizontal well like we do today in these shales, and we were trying to understand how fractures initiate. So this was using dyed water, and I won't go into all the detail. There's some perforations below and perforations above, and we're looking at these fractures and how they're initiating out of this particular case. It's actually a very complex initiation process. We expected to see one fracture coming out, and in fact, if you look closely, you can see there's a fracture here. Underneath it, there's a fracture. Underneath it, there's a third. Underneath it, there's a fourth. Underneath that, there's a fifth. There's actually 5 fractures sitting side by side, breaking out away from this wellbore, which no one ever expected to see. Here's what happens when a fracture hits a natural fracture. It runs into a natural fracture. Here's a case where it offsets a little bit, then continues on its way. But it gets a little more complicated than that. Before it offsets, it splays into a couple separate fractures and then continues on. It's the geology, again, that's getting into play here, and having some control over what the fracture is doing. And then just another case of another horizontal well, but this was an open hole one, dyed water again, and it's fractures going across layers and trying to understand, okay, if the layers change, how does that affect what goes on, and what we learned about fractures and their behavior based upon that. And I think the lesson everyone learned from this, from looking at this, was the more complicated the reservoir, that is, the more complicated the geology, the more complicated was the fracturing that we saw. So we actually then started to get into more sophisticated models in the late 1980s with trying to do it in 3D. And I just put some of the names down here. I'm not going to go into those. Some people who are familiar with fracturing would know those names. But the real focus in that time when trying to do the 3D modeling was fracture height growth, which of course is one of the focus areas right now that people are asking about. How high do fractures grow? And what can we do about that? And we knew from doing these mine back tests and all kinds of other work that stress and modulus of the various layers was really what the controlling parameter was. But the real problem we got into is kind of illustrated by this picture right here. This is a picture of the Utica Shale. It's an outcrop in Canada. And this is what the shales look like. And what we see is, if you start at the bottom, there's kind of a really shaly section down here that's maybe, I don't know, 6 inches or a foot. Then there's a carbonate section. Then there's a shale section. Then there's some kind of a clay-rich section. Then there's a carbonate section. And there's little clay sections in between. It's a real hodgepodge of layers. It's layers after layers after layers. So these are very complicated reservoirs. And trying to understand the fracture through them It really depends a lot on this layering and how this layering affects things. And then this also affects height growth. As you try, think of this like a composite, right? We build composites with all these layers to try and stop fractures from growing. It's hard to propagate fractures across all these interfaces and all these different layers, much like it's hard to create fractures that go across composites. So with all that in mind, this is where we start getting now into the diagnostics, and it's kind of really the heart of what I'm going to be talking about for the rest of this, is trying to figure out, okay, how do we get more information about these fractures? Trying to do modeling is nice, but we're not getting the same results out of them that we think we're getting, and let's try and figure out if we can monitor how fractures behave. So this is a case, I showed a couple things up here. Some of the early work was looking at the pressure. One of the things we measure all the time during these hydraulic fracture treatments is the pressure. And so can we analyze the pressure data to understand what's happening? And in fact, this was one of the just an early plot of one of the analyses that was done, pressure decline analysis it was called. And it's a very useful tool, and it's still used today. So it goes into the modeling kinds of work that we've done. But it really got into more of the other kinds of diagnostics, the geophysical diagnostics. And this picture here is out of the literature. This was from Los Alamos hot dry rock. They were doing geothermal work. They were injecting into a geothermal reservoir, trying to create fractures in that reservoir. And they were monitoring it with geophones to determine little creaks and groans that were happening in the rocks. We call it microseismicity. And from that, and where it occurred, they could actually get a picture of where the fluid was going and where the fracturing might be occurring. So this is a plan view up here. There's a couple of wells. These things here, these triangles are wells. This is a side view, kind of looking down the length of the fracture. This is a broad side view of that fracture. And this really didn't work out very well. This was at Fenton Hill in New Mexico. It didn't work out very well, but it gave us great ideas for, okay, this is how we're going to monitor hydraulic fractures. And it really started a lot of the research into microseismicity and how we use that to understand how fractures behave. But at that time, we still needed a lot of other information that we didn't have. So the Department of Energy also funded a lot of research wells, and probably the most sophisticated one was the MWX experiment. And this is here in the Piceance Basin in Colorado. It's about 9 miles west of Rifle, just south of the river. You can see this picture here. You can see handle points in the background. You can actually see the river right here, just a little hint of the river back there, where they drilled 3 wells. They took 4,000 feet of core. Core is the rock you can pull out after drilling. We could use an annular cutter on the drill bits. We used extensive logging and 5 years of testing and stimulation of these wells. So a huge amount of research to try and see, okay, what are the properties of these rocks? What do we do when we stimulate them? What can we measure? What's going on? And I put these 3 graphs up here because they're really important in understanding what's happening in these reservoirs. The one on the left is permeability, and you probably can't read it, unfortunately. It's permeability as a function of depth, and this is throughout the whole Mesa Verde section. And this is, every one of these symbols is an order of magnitude difference. And the whole point of this, and I won't go into a lot of detail, is that if you look at this core data, look at the rock itself, make measurements, it's extremely low permeability, 1 microdarcy or less. That's hard to flow anything through. It's very low permeability. If you actually do well testing and try to understand, well, what does it appear to be based upon what's coming into the wells, it's more like 10 to 100. It's maybe 1 or 2 orders of magnitude greater. And that's because of natural fractures. And this is a plot of the natural fractures as a function of depth, so we actually had a lot of information about those natural fractures. They're key to production in these sandstones. They're key to production in the shales as well. They're an important part of understanding how the fractures behave, understanding how we produce gas from those fractures. And then this one on the right has to do with stresses. And this is actually very important from the point of view of fracture height growth, which obviously we're all very interested in. And it's a little hard to see. Each of these symbols down here is 2,000 psi, so there's huge changes in stress as you go from one symbol to the other. That's a very large change in stress. It's a function of depth going from 4,000 to 8,500 feet. And if you can see the colors, the red colors are the non-reservoir rocks. They're like shales and siltstones and mudstones. And the blue colors are the reservoir rocks, like the sandstones. And what we would find, and you can find this in almost every reservoir, is that the sandstones, the reservoir rocks, are lower stress than the other rocks that surround it. And as a result, what we would see was fractures do not propagate very far because they want to propagate in the path of least resistance. They don't want to propagate in the high stress zones. They want to propagate along the length of these lower stress reservoir rocks if they all can. And there's a lot of other complications involved with that, but it sure gave us a lot of information about how fractures behave, having this kind of information about the rocks and the reservoirs in this multi-well site. And I just put up one other slide. I'm not going to spend a lot of time on this, but there was a lot of additional science done in trying to do some of this microseismic monitoring to try to figure out, can we see where fractures go? We actually put an intersection core hole through there to try and find the fracture, and this is what that fracture looked like. You can see all these fractures you see right here are all part of the hydraulic fracture. Over about a 4-foot length of this core, we saw something like 30 separate strands of this fracture. So this is something very complicated. It's not just one simple planar fracture. It's much more complicated. And a lot of production analysis trying to understand where the gas flow that I really won't get into, but a lot of science that help people understand how these rocks behave. And particularly the rocks, the tight gas sands that are all across western Colorado, certainly were a part of these kinds of studies. I say onward diagnostics here because I think even from the multi-well side, if I go back real fast, even from this picture, that's not a very clear picture of what's happening with the hydraulic fracture. This is a side view, and we're trying to see how high this fracture grows. Well, we have a pretty good idea, but a length view, we had a monitor well up here, we couldn't see very well. We needed to do a better job. And if you looked at the same time at some other tests that people were doing, a lot of people had the same idea. They're all pretty marginal in terms of the quality. And really a lot of the research that was done next was try to develop a system with multi-level receivers, high fidelity capabilities, downhole digitization, wideband telemetry, computational capabilities. All this technology was just coming into being at this time. This is in the late, well, probably about the early 1990s when this was. And it allowed us to actually go a lot farther and really understand how these fractures behave. With that in mind, we go back to some funding, again, from the government, from DOE, but primarily from the Gas Research Institute, who really drove this. So they were a funding agency who used a mill levy on pipelines to support research for oil and gas, both end use and extraction and everything else. And they funded at the same site, at that same multi-well site in the Piceance Basin. Now we're actually doing some additional work up a little shallower and trying to understand, can we figure out how to monitor fractures and know exactly where they're going. And so this was a multi-well test where we had a treatment well right here where a known fracture orientation kind of indicated in this plan view plot in this direction, going a little bit north of west, a little bit south of east. Some various wells with all kinds of instrumentation in them, and that's what this kind of illustrates. There's lots of geophones were put in here and tilt meters and all kinds of other instruments to try and measure what was going on. And the idea was to do the validation necessary to improve microseismicity and some of these other technologies to see if we really could monitor hydraulic fractures, because it was something really important, not so much at that time from the environmental aspects, because no one really cared about it, but from the engineering aspects. How do we improve this technology? How do we make it economic and extract natural gas from it in the best way possible? And here, I just put up one slide. I could actually have about 10 or 12 I could put up, but this is just one that illustrates that I just kind of want to indicate what we saw and the kinds of things you would see then and doing these microseismic tests. So here's a well, you really can't see this right there. It's the treatment well we're actually going to fracture. And these are microseisms. All these dots are microseisms. So these are little creaks and grows that happen in the earth because you're opening the hydraulic fracture and the earth moves a little bit and shifts and just makes these little seismic noises that we detect and we can locate. What was done in this particular case is from a place right here, we drilled down and then drilled over with a deviated well, about 55-degree deviation, and crossed the interval that we were going to fracture. And then we put a packer in there so we could pressurize that, build the pressure back up to the original reservoir pressure with a pressure gauge down there. And when we started fracturing, we would watch the microseisms, and we would know as soon as we saw pressure in this well, that's when the fracture got out to this point, 300 feet away. And at that time, we compared the microseismicity with where the known well location was to see how well that length compared. And this is what the data looked like. And there was really, really good agreement in this particular case, saying the microseismicity was mapping out the length of the fracture. So giving us some good validation, and yes, we can see what the length of the fracture is, and we have a pretty good estimate of what it is. Probably plus or minus 10% kinds of numbers, but that's really accurate for these kinds of geologic processes. We did other things. We drilled wells across some other zones, and we pulled core to see what those fractures look like. Here's another case where we had, I think, 11 separate fracture strands. So again, we're seeing a little more complexity and these kinds of things than we think. We did some other work with tilt meters to show that fracture height was agreement there. So a lot of good validation with a lot of science to show that, in fact, we did have some pretty good understanding of what's happening. So that led actually to a microseismic monitoring service industry. There's a lot of this going on nowadays. There's probably been tens of thousands of these fractures that have been monitored now with microseismicity. And the way it's done is you put in a string of very sensitive receivers into a well that's nearby. You listen to these little creaks and groans with triaxial geophones, so there's geophones in 3 different directions, so you can actually figure out which direction the sound is coming from, send it all up to the surface on fiber optic wire lines, process the data, and try and map out what these fractures look like. And rather than a schematic as shown here, let me just show you some examples. I put these in here just kind of examples of what you might see in some of these sandstones. These are all in Colorado. These are both. One is in the Grand Valley field in the Piceance Basin, and this one's in the Man Creek field in the Piceance Basin. And we're looking at, this is a case where there's a treatment well here and a treatment well here where we're fracturing these, and I think there's like 12 different fractures in each of these, and monitoring from wells here. You're seeing the kinds of fracture lengths we see, which is really important, right? We're trying to optimize fracture lengths. And same thing in the Piceance Basin. You're probably more interested in this side here. This shows the side view, and it gives some idea of, well, what do we see in terms of fracture height growth in these reservoirs? And these are sandstone reservoirs. These are not the shales. I'll show you the shales in a minute. And so you see what happens is these are the locations where the fractures are initiated. These are perforation intervals. So there's 5 in this particular stage, and these are the microseisms in blue. And this is an offset well where we know where the sands are. We're trying to follow these things along the sands. And we don't see much growth upward and downwards. We tend to see things going laterally. And what happens is they want to stay in that sandstone as long as possible, but that sandstone has limited extent. So it ends, the fracture will break out, but usually when it finds the next sandstone, it's going to propagate through that. It wants to stay in these low stress sandstones because it's just an easier path for it to propagate in. And we see this over and over and over again in these sandstone reservoirs. Okay. The Barnett sort of changed things quite a bit. This is the first microseismic test that was done on the Barnett. It was a very researchy type of test in 1997. And we looked at this and said, what does this mean? This is a plan view. There's a well right here that was fractured with a fairly large frac. And microseisms don't look anything like a fracture. There's just this huge blob around there. And even inside you, it's hard to tell what's happening. And in fact, we thought the test was a failure. We didn't understand it. We hit a fault. Did we do something wrong? This isn't working. We just don't understand what's happening here. And for a while, no one was really quite sure what to make of this and what to make of the microseismicity there. But we quickly learned when we finally started getting out there with some of these more enhanced systems that, wow, that's the way some of these shale reservoirs behave. So this is a vertical well with a large water fracking. That's what's being done nowadays in a lot of these shale reservoirs. They're pumping these huge water fracks with water and sand. And rather than seeing some fracture that you would see some elongated fracture that looks like this, like we see in the sandstones that I just showed you, things go all over the place. They get into the natural fractures, and they don't just go in one direction, they go laterally as well as they open up the natural fractures. And that's actually good. Actually, we need that. That's the only way we can contact enough reservoir rock to actually produce from these shale reservoirs. And then this one down here shows one of the very early horizontals. Nowadays, the horizontals will have 10 or 12 or 15 fracture stages in it. This is one that had only 2 stages. So there were 3 sets of perforations here, and stage 1 is shown by the blue. 3 sets of perforations here, stage 2 is shown by the red. Observation well is here. It's a long ways away to see all this stuff, so you don't see a lot of the microseismicity out here. But from just looking at this last stage, the stage 2, you can see things are getting all over the place. And that's very different from what you would see in the sandstone reservoir or some of the other typical more reservoir rocks that we deal with as opposed to the shales. Oh, come on. So where does that leave us? So this is an example now of what's being done. So this is what you'll see all the time if you were to do microseismic monitoring in a development in a shale reservoir. This is a Marcellus case. It's one that's been published in the SP literature. Basically, it's 2 horizontal wells. This is a plan view of 2 horizontal wells. Each well had 7 stages, so there's 7 different colors indicating the microseisms from each stage. Each of these stages had 5 different perforation clusters, so the way a well is completed, you actually put the casing in there, you cement it in, and then the zones you want to fracture, you actually shoot perforations through that to open those up, and then you fracture through those. So there were 7 sets of those in each of these wells. And what we're trying to do is we're trying to get transverse fractures. We're trying to get fractures that go orthogonal to the direction of the wells. That's the easiest way to contact the most reservoir. We want to make sure that they're close enough together. We have enough stages that we can actually fracture all the rock and not leave gas behind. We want to make sure that they're close enough that we can really kind of get these things close together and be able to fracture all of the reservoir that we possibly can. So this is really done for engineering purposes. And also looking at the side, looking at fracture height and trying to figure out, well, can we pump at different rates if we need to try to minimize fracture heights? What should we do with proppant? Are there other ways to try and to change what the fracture height is? But that notwithstanding, from an engineering point of view, this also provides a lot of very valuable data for the environmental purposes. That now we know what the fracture heights are. We have measurements of these fractures in many, many of these shale reservoirs and other reservoirs that tell us where's the bottom of these fractures and where's the top of these fractures. And that provides a lot of guidance for the environmental questions that are being asked. Before I actually get into the environment, I'm going to end this talk here just a couple minutes with environmental kinds of things. But I want to just mention that what's happening nowadays is we're bringing a lot more tools into this problem. That even microseismicity doesn't tell us all the things we want to know. So the effort now is on more research, on more kinds of tools, trying to bring in fiber optic technology like distributed temperature sensing, distributed acoustic sensing, and we'll have all kinds of other types of fiber optic sensing probably within the next 3 or 4 years. And so what happens is you put a fiber in the whole length of the wellbore, and you can send pulses of light down that, and from the reflected light that comes back, you can tell what the temperature is all along the length of that wellbore. You can hear where sound is coming from all along the length of that wellbore. And it gives you tremendous diagnostic capability to understand what's going on along the wellbore, where are you producing gas, where are there leaks if there's a leak, where is fluid flowing. So all those kinds of things now are becoming doable in terms of monitoring fractures and monitoring wellbores and their behavior and those kinds of things. This is an example of this is first of all an example of the temperature. So this is a horizontal well in the Barnett. And we're looking, while pumping, we're looking at everything's cool. It's actually going in this place right here where it's very, very cool. And there's actually been a valve shut in right here, and it's warming up behind it. And you can actually do an analysis of what we call this warm back profile and tell where this fracture is and how much of the fluid looks like it's in that fracture. If there's more than one distributed, how much is going on. So you can actually tell quite a bit about what happened with that fracture treatment from this temperature data. But another one that's also very valuable is this DAS, distributed acoustic sensing. So this is listening to noise, basically. And the wellbore actually goes like this. It's not clear from here, but the wellbore is along this direction, the vertical direction. This will be down towards the end of the well. This is back towards the wellhead. This is one fracture stage that had 5 sets of perforations in it. And this is time going off to the right. And all we're looking at is noise. So these bright red colors are where it's noisy, and the other colors, the blue, is where there's no noise, and the green is maybe a little bit. And what you can tell is which ones of these are taking fluid. So obviously the top 3 are taking lots of fluid. This next one down is taking a little bit less fluid. The bottom one is taking hardly any fluid. We can do that on injection to see where the fluid's going. We can do that on production to see where the fluid's going. So it gives us a lot of information about what's happening in the wellbore. And since these can go all the way up the pipe, you can see if there's any leaks or anything else that's occurring and tell exactly what's happening with the fluids. And then there's other tools like tilt meters and things that allow us to see the deformation and understand how the fractures are behaving from deformation as well. So let me finish up here, getting close to that time, and talk about the environment a little bit, because that's obviously one of the questions that's on everyone's mind. First of all, I put this picture up because it puts things in perspective. If you have a horizontal well, this is a typical Marcellus example, you have a horizontal well that's going to go about a mile and a half down, and then it's going to turn horizontal once it gets down there and extend maybe for another 4,000 or 5,000 feet. And this would be a vertical well, which really isn't done very much in a lot of these shale reservoirs. And then the fractures, and you probably can't see it very well, the fractures are typically on the order of maybe 400, 500, 600 feet total fracture height. And you can see where they are relative to the aquifers. So the aquifers would be up here, 200, 400, 800, 1,000, maybe 1,500 feet, maybe as deep as 2,000 in some cases. But nowhere close the fractures come to the aquifers. Well, how do we know this? How do we know that these things are really just 400 feet? Now, I'll get to that in a second. I actually have a plot of that from all this microseismic data. But I want to come back also that this is really where people ought to take notice and look at what's going on there. It's the well construction around the aquifer. And that's something that is really dictated by the states. The states, they do the permitting for it. There are regulations on how you have to actually case off that the aquifer zone, how deep you have to get the surface casing, the cement, how many different types of intervals you have to have in there. So that is all information that is really important, and it is dictated by the states. And every state is different, right? They have different geology, so they have to come up with different regulations, different depths they have to work to, and all those kinds of things. And if there's going to be problems, the problems are generally with the much older wells, because a lot of the older wells were done before some of these regulations came into effect. And it's going to be the older wells often that are the problems as opposed to the newer ones. But anyway, back to this question here. So if we look at this area here, and how do we know that these fractures are only a few hundred feet tall relative to the aquifers up there? Well, I have a plot of microseismic data, if I can get to it. And it's, I'll spend a couple minutes on this plot. It's a little bit complicated. It's depth over here on the left. This is in feet, so thousands. Every one of these is 2,000 feet. This is the number of fractures we monitored, so not quite 7,000. This is data up to, I think, mid-2011. So that was all the data we had from these 6 reservoirs at that particular time. And what this shows is it's sorted by depth. So we're looking at the deepest reservoirs down here, which would be the Haynesville as an example, and some of the deep parts of the Eagle Ford would be down here. The Barnett would be in this region. If we had the Niobrara here, it'd also be kind of down in this region down in here. Some of the Marcellus actually gets some of the shallower stuff. It's probably Marcellus. But what we have here is if you look at the black line in the middle, that's the depth that the fractures were initiated. So these are mostly horizontal wells. That'd be the depth of the perforations in these horizontal wells. The green shows that it drops down to the deepest microseism, which we've taken to be the bottom of the hydraulic fracture. And the red is the shallowest microseism, which we've taken as the top of the hydraulic fracture. And so we get a pretty good idea of what's fracture heights as a function of depth in all these different reservoirs. And we can, I think I have a slide next that actually breaks it down for the Barnett Shale. You can see a little more detail. But you get a pretty good idea that, yeah, sometimes you do get some fairly significant amount of fracture height growth. You can get 1,000 feet of fracture height growth, and even in a few cases, 1,500 feet of fracture height growth. But the aquifers, those typical depths are somewhere way up here, and none of these come anywhere close to the aquifers. Some of the interesting things we see is that, and it's not quite so clear here, it'll be a little clearer in the next one, in most of these reservoirs, as you get shallower, you tend to see less and less height growth. And there's good reasons for that in terms of the stresses. If you understand the way the stresses behave as you get shallower, you'd expect that to happen. And in fact, we see that it does happen. But the first thing people, when they see this, they ask me, well, what happens if you get into a fault? Gosh, if you get into a fault, it's just going to go up, it's going to go wherever it's going to go, it's going to go a long ways. Well, the truth of the matter is probably about 20 or 30% of these fractures got into faults. We see it get into faults a lot, and it's pretty easy to tell when you get into fault. Things go in different directions, and the magnitudes of the vents you get, the amplitudes get larger, and it's pretty clear that you get into faults. And some of these spikes are faults. You will see a little more fracture height growth if you get into a fault. It may go down more, it may go up more, it may go sideways more. So you can get into faults, and you can change the behavior of the fracture a little bit. But even with that, you don't inject enough volume. There's no way that we've seen any of these get anywhere close to the aquifers that we see up there. So even with the cases of faults and all those kinds of geohazards, we never see any sign that we're generating fractures that extend much higher than maybe 800, 1,000, or 1,200 feet above where the fracture was initiated. It's just really, really difficult to do anything other than that. And here's just there's a lot more detail in this, and I'm not going to go into it. But this, if you look reservoir by reservoir, if you looked at the Barnett Shale, this is what you would see. And this is by county, by county, by county, and the aquifer depths are by county. There's just a lot of data here that I won't get into. But this, I just pointed out because this is one where it's pretty clear as you get shallower, you get less fracture height growth because of the changing stress conditions as you do get shallower. By the way, as you get shallower, what happens is the stresses change, and instead of getting vertical fractures that want to go up and down, the stresses change so you get horizontal fractures. You actually start lifting the overburden up, and you don't get fracture growth going upward anymore. You get fracture growth going sideways, and what we call pancake fractures or horizontal fractures. Okay, one more. I think there's one more set of data here. I can get to it. So the last thing I want to talk about is induced seismicity. People are worried about earthquakes, right? And they bring hydraulic fracturing into it. And really, we know that if there's an issue, it has to do with long-term pumping into reservoirs. We saw that with Rocky Mountain Arsenal, where they were pumping waste for many months. We've seen that with the Paradox Valley project, where they're doing the saltwater disposal to try and get rid of it to keep the water as fresh as possible in the Paradox Valley here in Colorado. And you see it in other places as well. And clearly, if you just keep injecting long periods into basement rocks, you can start to generate some earthquakes. But the question comes up, well, what about hydraulic fracturing? We're injecting with hydraulic fracturing. What happens in hydraulic fracturing? This is an example of what the waveforms look like in hydraulic fracture. There's a compressional wave we call a P wave that comes in first, a shear wave comes in later. You can analyze that exactly the same way the seismologist would analyze an earthquake and look at the amplitudes, and from that in the spectrum of those amplitudes, and you can figure out what's the magnitude of that event. What was the amplitude, what was basically the strength of that event at the source. That's what the magnitude is. And this is a plot of what we see in hydraulic fracture. So this is up to about probably mid-2012, I believe. It's the 6 major reservoirs in North America, again, where most of the shale work has been going on. It shows versus, this is a histogram, so this is frequency. So this is the number of tests, and this is moment magnitude. Now what's plotted here in this histogram is the largest microseism observed in terms of its magnitude for every test. So let's say I did a hydraulic fracture and I had 300 microseisms. I would take the biggest one and put it into the database that goes into this plot. So these are just the largest microseisms for fracture. Most of the microseisms are way down here in this area, the low end of this. So what do we see? We see that generally the largest microseism we see is a -1 magnitude. Okay, well, what does that mean? This is a lot like a Richter magnitude. A moment magnitude is very similar to what the thing you're familiar with, right? With earthquakes, a +3 is a typical event. You just start to feel at the surface. Wouldn't cause damage, but you just start to see it. This is a log scale. So going from a 3 to a 2 is actually a factor of 32 difference in energy. Going from a 3 to a 1 is 1,000 difference in energy. Going from a 3 to a -1, the kind of average we see, is a million, factor of a million smaller amount of energy in that kind of microseism. This is probably the important point, though. In all these sedimentary basins, which are all quite relaxed, we tend to see nothing bigger than about a 1. That's about as big as we get. That's very, very little energy in these little microseisms that are occurring. Someone said, well, is it possible to get bigger ones? It's always possible. There's a case in the UK, Quadrilla was doing, they actually drilled a well into a fault system and started injecting into it, and they got a 2.3 or a 2.5 or something in that order. There was another one up in Canada where they actually drilled into a fault system again, and they were getting into the 3-point range. And so it is possible in some unique circumstances. Usually down here in the U.S. in the sedimentary basins, we want to avoid faults. We avoid geohazards like plague, so you don't normally want to do that. But certainly it's possible. But in general, in all the development that's typically done in these reservoirs, we really see no indication that there's any kind of earthquakes that are generated of any significant size. So let me end the talk with that. And I guess the last thing I want to convey is, and that's what kind of all these pictures are hopefully there for, is that there's a huge amount of science that has been done. I started out with a relatively small group of industrial and academic scientists and engineers. I was telling someone earlier that there were probably, in the 1980s when I was doing a lot of this research, there were probably 200 of us maybe, or 300 at the very most. And everyone knew each other. Everyone was very good friends because we were such a small community doing hydraulic fracturing research. And that's not the case nowadays. There's thousands of people working on hydraulic fracturing. But there's a ton of information about fracturing that's out there in the literature. A lot of it's in the petroleum literature, a lot of it's in the rock mechanics literature, some's in the geophysical literature, but it's out there. So if people want to understand what do we know about fractures, what have we seen in all this research, what has the government-funded research showed us, a lot of it's been published. It's been published in journals, a lot of it's in government reports, but all this information is out there. So there's a lot of science that's available for people who really want to know more if they're interested in it. So with that, I think I've used up my time, and I'd be happy to, oh my, look at all those questions.
You have questions. Thank you.
Let me get a drink of water.
So yes, you do have some questions here. I think we'll start in with some general questions about wells and, well, actually, let's not do that. Let's start with some facts about fracking. Some of these are about scale and size. What's the largest fracture distance you've seen from a horizontal well? In what basin do you see the longest fractures?
Probably the longest fractures we've seen have been up in Canada, in the Muskwa, which is in the Horn River Basin. So that's up in the far northeast corner of British Columbia. Some of those fractures we've seen have been on the order of maybe 2,000 feet wing length. So total length would be 4,000 feet, 2,000 feet in each direction. In general, I would say that here in the Barnett, we might see some that extend out 1,200, 1,500 feet laterally on each wing. but most of them are much less than that. Most nowadays are maybe extend out 1,000 feet or 700 feet or something on that order. Now, I assume that means length. Height generally is more like 400 to 600 feet. Occasionally you get 1,000 feet of fracture height growth, upward and downward.
This one, I think this question was probably written just as you were making your shift from sandstone to shale. So how far does a fracture run in shale and hydraulic fracturing? Although your point may have been that, if I have this right, that it's kind of harder to say for...
Well, so there's a couple parts to that. So it is a little harder to say because fractures in shales are a little more complicated. But there's something else. We actually create a lot smaller fractures now in sandstones than we do in shales. And the reason is because these sandstones tend to be much thinner. If you look at the shales, many of these shale reservoirs are 200 feet thick. And so we have to put a lot of volume in there to get fractures that are big enough in those shale reservoirs. Plus the permeability is lower, so there's not as much gas flowing through it, so you need much more surface contact area. The sandstones, you're probably just wasting fluid if you try to extend fractures more than maybe 800 or 1,000 feet, because you're probably going to get into other reservoirs, you're going to do other kinds of things. So we tend to pump smaller volumes, we tend to pump at smaller rates in sandstones. Many times we're vertical wells in sandstones, which also tend to help us actually keep things a little bit smaller. We tend to pump smaller fractures in vertical wells. So there's a lot of different things going on there as to why the sandstones are different than the shales.
How wide are the cracks that are generated by the fracking process?
Yeah, that's a good question. So, when we did the mine-back test, what we typically would see we did a number of tests with proppant, just like you would do in the oil business with a gel and a proppant carrying it. And those were typically on the order of maybe about half a centimeter wide at the widest part. We did a number of tests at the Nevada test site as well. We actually used cement because we actually wanted to keep the width of the fracture. We didn't want it to close up. And if you use a low water loss cement, it would actually not close up. And in some places we saw the fracture as wide as a centimeter there. Now, from all the modeling we do nowadays and trying to understand what's happening in these fractures we're doing now, probably half a centimeter is probably a typical fracture width that we get in these reservoirs.
What is a frac hit, and does it cause a problem? Do wells get damaged by a frac hit?
So yeah, that's a good question. There's no one answer to that. So a frac hit is when I have a well over here and I'm producing it, and all of a sudden someone comes over here and they're doing a frac job at another well, and their fracture actually intersects my well, and I start producing frac fluid out from that frac hit. It's called a hit. And the question is does it do damage? Actually, in a lot of reservoirs, once they clean up that well that was hit, it actually produces better most of the time. And the reason why is now it's got this new fracture that it connected to, so even though that's draining back into the other well, it's also giving them reservoir contact into that well. So sometimes fracture hits actually improve production of wells. Other times they load it up, they can damage the well, and it can actually decrease production. It's dangerous in the sense that you really want to know if someone's fracturing nearby, because there's obviously safety concerns, and there could be other concerns as well. In oil wells, you don't want to have oil coming out because someone actually hit your well. So there are concerns about that need to be worked on.
What is the average time it takes to fracture a single well? Is it 3 to 5 days on average?
That's a tough one because there's different types of completions. So if we're doing what's called plug and perf, a typical frac job might be 2 hours long, but then it probably takes another 3 or 4 hours to run down the plug and the guns. So you plug off that interval, the perforation guns are then shot, so you actually have the perforations in the new section, and then you have to pull that gun out of the well, and then you start fracturing that. So it might be 5 or 6 hours for each fracture in that horizontal well. So if you have 10 fractures, you now have 60 hours. If you have 20 fractures, you might have 120 hours. So it depends how many stages are done. That's the longer type of completion. There's another completion that's an open hole completion where you just use sliding sleeves, and the way it's done is once you've done one fracture, you drop a ball down. The ball, because you're pumping at the same time, is pushed down and actually seats in a valve, and as it closes that valve, it opens up the next ports, and you can just go right into fracturing the next zone. So if you have 2 hours of fracturing, maybe a short period where you're pumping down the ball, maybe 20 minutes or half an hour or something like that, 2 hours of fracturing, another short 20 minutes to pump down the next ball, 2 hours of fracturing, that goes a lot faster. So that goes at maybe 3 times or 4 times as fast sometimes.
Now we have a couple of vertical well related questions. Can you comment on the, let's start here, wait, excuse me. So hydraulic fracturing was combined with horizontal drilling in the early 2000s. Do you believe combining these technologies presents more or less risk than hydraulic fracturing with vertical wells?
I would say, I have to say less risk for a number of reasons. So first of all, if I'm doing vertical wells and I need to have a well, I need to have a fracture every 300 feet, and I have to do that by drilling all these vertical wells, and well construction is the bigger issue, then I'm putting in a lot of vertical wells that I have to go through the aquifer in every single one of those. Whereas if I have a horizontal, I have one well with maybe 20 fractures in there instead of 20 vertical wells. So from the perspective of just how many wells are being drilled and well construction being the bigger part of the problem, I would say horizontal is a much better situation. And plus, if you have 20 vertical wells, think of your environmental footprint at the surface. You have all these different pads for 20 wells as opposed to one pad for that single horizontal well, as well as all the other operations that go alongside of that. So I think from an environmental standpoint and a risk standpoint, I'd much rather have the horizontal situation.
Could you comment on the ability of the vertical well casing and cement to resist transverse stresses and forces?
The ability of the vertical well to resist?
I think just your central well bore.
I'm not sure I know exactly what that means, so that's a tough one for me to answer. I don't think, there's a lot of stresses on wells, obviously.
Actually, while we're stressing you with that, what about the stress on the well casing? So that might, I think
right, so they're all related. So as you pump down at high pressure, obviously you're putting stress on the casing, which is putting stress on the cement around that. And so the question is what does that do to cement integrity, and can that be a problem? And what we usually find out is over a long lifetime, it's possible that things could start to deteriorate a little bit, and you start losing some of your integrity, but not a lot. But what the good news is about all this is that where this is liable to be the worst problem is down near the zone that you've actually fractured, and there's where your pressure is the lowest. So it's not like you have high pressure that's trying to push fluid up your well bore. You have the lowest pressure down there around the zone you're producing, and it's actually trying to draw in fluids from all around there because it's the low pressure sink. So you've actually reversed the situation. Everyone always thinks, well, I have lower pressure at the surface, all my fluids are going to go up that way. Not around a producing interval. If you're producing it, that's the low pressure sink. That's where the fluids all want to go, and so you're not going to have fluids tending to migrate away. They're going to be tending to migrate into your well.
Okay, on well permitting, in what scenarios should fracking be avoided? And I guess, I'll just ask you that. Okay, in what scenarios should fracking be avoided? Are there circumstances, you've mentioned that lots of variations in geologies. Are there some kinds of geologies or some kinds of structures where it's just too much trouble?
There's certainly people issues, right? That if you're in the middle of a town and you're going to put a well right in the middle of a subdivision, is that something that you want to have happen? And I think there's a lot of people who say that that's probably not a good situation. Let's take the well somewhere else and try and put it elsewhere. I think the people issues at the surface are probably the more important ones. Most of these reservoirs we deal with are reservoirs, at least from the hydraulic fracturing standpoint, we're putting in large hydraulic fractures, are all fairly deep reservoirs. I don't think there's any that are going to be less than maybe 2,000 feet. And that's maybe the Fayetteville, which is fairly shallow reservoir in Arkansas, and parts of the Marcellus as you get into New York actually get a little bit shallower. So from the geology point of view and from the depth of these reservoirs, I don't think there's an issue. I think the only other issues are things that, how do you deal with people and things that affect people, probably the more important ones.
This takes up something you'd spoken about, the avoiding faults. Should fault mapping be considered in the well permitting process, especially regarding allowing hydraulic fracturing? So should fault mapping be in the permitting process?
So what we've seen is we've seen no significant effects of the faults on any of this mapping that we've ever done in terms of being an environmental problem. Sometimes it's a problem for an operator because instead of fracturing right here, they're fracturing way over to the side because they got into a fault and there's just stuff going on off to the side. Sometimes it goes a little higher, sometimes it goes a little bit lower, but it never seems to be a problem from an environmental standpoint. I would say if you had a major fault that extended all the way to the surface, first of all, everyone's going to know it's there, and they're going to avoid it. And usually what happens is if you have a major fault that extends through your interval and all the way to the surface, the gas is all gone. Over geologic time, it's going to have migrated out of there. No one's going to be drilling around there because there's no gas there. If you have a fault, the gas is gone, the hydrocarbons are all gone, they've all escaped. So I would say that where it could be a problem, everyone knows what the situation is and nothing's going to happen. And the smaller faults, where they really wouldn't know where they are, never seem to be an issue.
This returns to your saying that the area close to the surface is the area of concern for where is the well fracking? How and where is in the well fracking process is methane and other gas escaping into the atmosphere?
You know, that's one I really don't know enough about. So are there fugitive emissions of methane? There's always going to be fugitive emissions. There's fugitive emissions from the pipelines that run underneath our city, but that's not something I've looked at, and I really don't have any answers for that particular question. You know, in the old days, we used to flare off a lot of gas, and there's still some flaring that goes on now, but that's burning it, so we don't have methane. We actually have, you know, the various byproducts of burning it. There's still a little bit of that goes on, but not nearly as much. I'm sure in the old days, it was probably lots of times people just open it up just to relieve pressure and just let the methane blow out. That doesn't happen anymore. There's a lot of rules and regulations about what you can do to the well and the way you have to treat a well. But as far as what it is now and how much we capture and how much might possibly escape out of it, I really don't know that.
Okay, here's a series of questions on the chemicals in frac fluid, beginning with, when did the use of chemicals begin? Was it initially water and sand, and when did the chemicals enter the picture? Yeah,
that's an interesting question, because actually the first chemicals used, the first fractures were done with what's essentially what was napalm. It was gel diesel, and it was actually a very good fracturing fluid. Very dangerous, but a very good fracturing fluid. And quickly after that, they also went to water and pumping water and sand. By the way, they did pump sand right with the first ones with the gel diesel, but very little sand was pumped at that particular time. Over the years, what happened was they started using less diesel and they started getting away from the water, and they went to these gels that we use nowadays. They're guar gels. So guar bean, which we use in all our food additives, is the main thickener that we use in hydraulic fracturing. And that was used widely through the 80s and even well into the 90s. And then all of a sudden we got into the shales, people started going back to water fracs where they use very little chemicals. Basically it's almost all water and sand, a little bit of friction reducer, which is the polyacrylamide, and you know, a few things like maybe a little bit of biocide. Sometimes they'll spot a little bit of acid, but not a whole lot of chemicals. But nowadays what's happened is in the gas reservoirs in these shales, it's almost all water fracs. In many of the oil reservoirs, there's a lot of gel being used, and they'll maybe use half, a lot of times they use a half and half, where they start pumping water and then they go to what they call a hybrid. They'll go to gel at the end, and sometimes they'll use gel throughout most of for the fracture treatment. So there's a wide variety. It really depends upon where you are in the reservoir you're dealing with.
What is the Halliburton loophole? We could not help but notice on your slides. Halliburton does not appear in that particular slide. No. But what is that Halliburton loophole?
There is no such thing as a Halliburton loophole.
What is that thing in the Energy Policy Act that a person who once worked for was supposed to be
they claim that Cheney somehow got, my understanding is, now I've not looked into great detail, my understanding is they claim that Cheney somehow arranged for hydraulic fracturing to somehow not be regulated. And the fact of the matter is that it had never been regulated at that particular time, and it was never on the books to be regulated. So it's been claimed to be a Halliburton loophole, but from everything I understand, it was never that. I mean, it looked that way, but it never was that way.
Well, following up, it is a public knowledge that the frac chemicals represent less than 5% of full frac volume. If that's the case, how do operators explain that they cannot disclose, or that even though that is only 5% of the material, why is it not easy to disclose that? Why would the operators not really disclose?
Well, I'm not a lawyer, so I can't really give a legal answer. First of all, it's 0.5%. In most of all these fracture treatments, it's 0.5% that's some kind of chemicals. Most of the chemicals are, they tell you exactly what's in there, provide sheets on what exactly the chemical is. There are a few chemicals that are considered trade secrets, and they don't want to tell exactly what's in there. But what they do is they tell you all the chemicals that are in there and provide MSDS, so the material safety data sheets are provided for each of those chemicals. What they won't tell you is what the exact proportions are. And this isn't just Halliburton, this is Schlumberger and all the rest of them. And the reason why is they have, in most of these chemicals, maybe not all, maybe some of them could be, but in most of these chemicals, they've done some kind of core research where they've looked at how these chemicals behave and how they interact with the rocks, and they find out that different compositions behave differently for different situations. And they want to tailor it to the particular situation. So there's going to be a particular percentage of this material, a particular percentage of this material, and a percentage of the third material, and they don't want to reveal that. They'll tell you what's in there, what all the chemicals are, but not what the percentages are.
How come you have spoken of water and sand, but not benzene, etc.?
Because nobody in this country fractures with hydrocarbons anymore. It's still done in Canada a little bit, but I haven't seen anybody fracture with hydrocarbons in quite a few years. So there used to be a lot of diesel fracturing, so people used to use that because it's actually a very good fracturing fluid. And just to give a little background on why it's a good fracturing fluid, is one of the last things you want to do in a reservoir is put in a new fluid. So let's say you have a hydrocarbon reservoir. If you put in a lot of water, now all of a sudden you're really changing the fluid content. If you put a hydrocarbon in that reservoir, well, it's just another hydrocarbon interacting with the rest of them. So things like diesel were actually very, very good fracturing fluids. And that's why propane, you heard a lot about gas frac, which is the non-water frac. It actually uses propane, and that's a very good material to use because now that's very similar to the methane that's in the reservoir already. So things like that are very good fracturing fluids, but because of safety reasons, because of the environmental reasons, the things like the diesels are not used anymore. I think they could be used. I think someone could actually apply to EPA to get a permit to do that, but I have not seen that done in quite a while.
Did they ever use chlorinated solvents, i.e. TCE, DCE, as a chemical additive in fracking fluids? And yes, when did that practice stop, or has it stopped?
I don't know. I don't know the answer to that.
Okay. What percentage of decrease in recovery of oil and natural gas would there be if only water and a proppant were used to frack? 10% to 90%, other?
What percentage decrease? Okay. There are some reservoirs where the decrease would probably be fairly small. So, for instance, the Barnett Shale, where we're doing these large water fracs, if we use no chemicals whatsoever, probably the two main problems I would guess is it'd be a lot higher pressures because we're not using a friction reducer, so it'd be more expensive to do that fracturing. So there would be economic costs, and there'd be the not using the biocides and those kinds of things, which could obviously cause some problems. So in a reservoir like that, probably not a whole lot of difference. But if you went away from it in, say, the Eagle Ford reservoir or the Niobrara or the Bakken, where they're using gels, and you didn't allow them to use gels, you get very different performance. And I think you could probably cut it down by 30, 40, 50% of the production, basically essentially making it non-economic if you did that.
So did the diagnostics did the diagnostics tell you what happens to the frac fluids and the chemicals that are added?
No, that's an interesting question. So the diagnostics tells us where the fracture is gone, but the question of, okay, so where's the fluid is one that, basically we do sort of a mass balance, right? We know how much we put in, that's measured very carefully, and we measured what we flow back. And most of the time, what we actually get out of the well after all the flow back is like 20 to 30%. So we're left with probably about 60, 70, 80% of the fluid still in the reservoir. What happens in these reservoirs is let's talk about the shales. The shales are the most interesting case. That's where all these big frac jobs are being done. In the shales, the initial water saturations in the shales are very low. They're desiccated essentially. And so upon contact with water, the water gets sucked into them. And so they'll call it imbibition. And what happens is as the water contacts the shale, it's getting sucked into the pore space in the shale, and it basically is there forever. What's called capillary pressures are so large, that stuff is probably never coming out, and it's stuck there forever because of the very tiny pore spaces and the large capillary pressures you get.
Sorry, I should put this in an earlier one, but I'll read all the questions. So, I'm repeating something. Why is the industry so defensive about releasing chemical info on frac fluid if it is generally harmless?
It's the trade secret aspects. Again, we're back to the trade secrets, and they will release what those chemicals are. You can find out exactly what those chemicals are. You'll get the MSDS sheets if you want, but you won't get the proportions, and that's what they won't release.
Okay, and now we have several that you have spoken quite a bit about, distance from aquifers, but I'm going to just read these, and if there's something that you want to repeat, or if you say, I think you covered it, that's fine too. How far below the water table in Colorado are they fracturing?
Colorado covers a lot of ground. You know, the Niobrara is fairly deep, and the Piceance Basin, that probably, and I've not been out there a lot recently, but probably 4,000 to 8,000 feet is where most of the activity is. Probably the shallowest places are probably in the southwestern part of the state, where they're doing a lot of the coal bed methane work, is probably where the shallowest activity is. But I'm not even sure exactly what the depths are that they're working at out there. But I don't know, maybe someone else knows. I really don't know for sure. I've not paid a lot of attention to the coal bed methane work out there.
In terms of the impact on the water table, does that impact present cons or opposing arguments to hydraulic fracturing?
To the water table?
Yeah, the impact on the water table.
There's as far as using water for fracturing, I guess, I assume is what was meant there, that we're actually going to draw water. You know, it sounds like we use a lot of water for hydraulic fracturing, and if you have a well that you pump 1.5 million gallons of fluid, that's a lot of water, or 2 million gallons of fluid, that's a lot of water. In terms of actual industrial use for power generation, for golf courses, for municipal uses, in most states it comes out to be less than 1% of the water that's used in the states, and much less than what's used in power generation, and certainly much less that's used in golf courses and things like that. So I guess the question is okay, if you don't want natural gas, then that's fine. We'd rather have golf courses and other things. It is a problem, obviously, that there's a lot of states where water is a much bigger issue than it is in some of the others. People are trying to work to use brackish water, so instead of just always using fresh water, there's a lot of companies now that are reusing water from the flowback, clean it up and use it. There's a lot of companies like Apache in the Permian Basin in Texas that are actually using brackish water, and people like the company I work for, Halliburton, have developed chemicals that will work now with brackish water. That's something that they didn't have many years ago. There's still some limitations to temperature and things like that, but in a lot of cases it can be used. So there's a lot of ongoing work to try and solve that water problem. And I think what we'll see is as we move forward, that there's going to be a lot less freshwater use in fracturing as we move forward.
This again may repeat territory we've already covered here, but how do fractures propagate in shallow reservoirs? Or I guess, do fractures propagate in shallow reservoirs? If the aquifer is 500 to 1,000 feet below the surface of the earth, and the frac zone is 2,000 feet below, is there a chance of that connecting?
So what we typically know about the stresses in the earth, and the people have done a lot of measurements of the stresses as a function of depth. What you see is below about 2,000 feet, we tend to see vertical hydraulic fractures. Basically, the stresses are such that the path of least resistance is to be a vertical fracture. There's a zone between about 1,500 feet and 2,000 feet where it's not clear exactly what's going on. It could be vertical, it could be horizontal, it could be some part of that. As you get shallower in almost all these sedimentary basins, shallower than about 1,500 feet, the stresses are reversed, and the stresses horizontally are much higher than the stresses vertically, and you end up getting horizontal fractures. And probably what really happens is it's probably not entirely horizontal fractures. All these different layers have different stresses in them because they have different properties and they have different loads on them, so each layer will have a little different stresses. And what we think probably happens is it's a lot more complicated than that. You can get a zone that has a vertical fracture, then you can get a zone that has a horizontal fracture, and then maybe you get a little vertical fracture, then another horizontal fracture, and so you can get a little bit of vertical growth, but it gets to be very, very horizontal in terms of its areal extent, and you know, very, very kind of complicated as far as the way it behaves, because it does have this interaction between these different fracture orientations. And that probably happens up to maybe 1,200 feet or something like that, and then above that we tend to see almost all horizontal fracturing.
For example, would it make sense to install monitoring wells at oil and gas well sites to demonstrate the impact or lack of impact to shallow aquifers?
I think the better situation is you take water samples beforehand and you take water samples during. if you want to understand if there's any potential effect on the aquifers. I mean, get a baseline, and in fact, a number of states actually mandate that you have baseline water samples, and that's the easiest way. Rather than drilling new wells, why not just use the wells that we have and get the water samples there?
Why are the allegations regarding hydraulic fracturing causing groundwater contamination, why do they continue to be made by fractivists, media, and members of the public?
I wish I knew.
Alternative degrees of journalism coming up pretty quickly. Now, Trace, what challenges remain in developing and implementing tracing as a way of testing and verifying the movement of fracking fluids?
So by that I assume they mean using tracers. And actually there's a lot of work going on with tracers. That people use a lot of tracers in the oil industry right now in trying to understand where they're actually contacting oil, where they're actually, the fluid is going and where it's flowing back from. So it's actually used quite a bit. And we actually look at tracers sometimes across wells. We do tracer tests, figure out where fluid is moving and how it's moving. So that is something that's actually being done quite a bit now. Not necessarily for environmental purposes, but just trying to understand the general flow behavior of these reservoirs and what's the effect of the fracturing on the flow behavior in those reservoirs.
Okay, here's one I'm just not going to pronounce it right. What Richter magnitude is a 1 moment, or moment magnitude? What is a 2.3?
Okay, so let's talk about it in terms of energy. If I can remember my numbers, I think the area we work in with microseisms, typically around a -2 is kind of an average microseism that we see. A -2 has an energy of 62 joules. So someone says, well, what's 62 joules? If I pick up a gallon of milk and lift it up about 3 or 4 feet high and set it on a counter, I've used about 62 joules of energy. So that gives you an idea of just how little energy that -2 is. Every time you move up a magnitude step, it's 32 times that. So then from a -2 to a -1 would be 32 times 60, whatever that is, 1,800, whatever that is, nearly 2,000, I guess. If I go up to a 0, that's another factor of 32. So you can, actually what happens is the easiest way to think of it, every time I go up 2 magnitude units, it's a factor of 1,000 increase. So if I start with the -2, that's 62 joules. If I go up to a 0, it's 62 kilojoules. If I go up to a +2, it's going to be 62 megajoules. So, not megajoules? Yeah, factor 1,000 megajoules. So you get some idea then up the scale. And what happens is because it's a log scale, once you get out to the 3, 4s, 5s, and 6s, the energy goes up very, very fast. And there are huge amounts of energy that are generated by these earthquakes. But these that we're talking about here for hydraulic fractures and these things are actually very small.
Do you know, or did you know, that the Colorado Oil and Gas Conservation Commission has a horizontal well offset policy and that it will likely become a rule in the near future?
No, I did not know that. I'm not that familiar with the Colorado rules.
Microseismic and other geologic monitoring techniques are very high-tech and very expensive. I would imagine, expensive, I would imagine. What percentage of regular unconventional gas wells, i.e. not experimental wells, are monitored and studied with these types of technology? And do you think that the percentage of closely monitored fracturing jobs is adequate?
It's probably on the order of a few percent. And I don't know exactly what that it was. A number of years ago, we estimated it could have been as high as 8%. I don't think it's that high anymore because there's so many fractures being done now in these horizontal wells because they've increased the number of stages and we're really not monitoring too many more wells. So I'm guessing it's probably maybe 3-4%, maybe as high as 5%, but not a lot more than that. What happens is they want to know what's happening early on in the life of the reservoir. Before they start doing their development and drilling all these wells and getting them going in the wrong direction and the wrong lengths and the wrong number of stages, find out early, do the science, figure out what's going on. And so what happens is you'll find out early in the life of these reservoirs when the company first gets in there, they'll do quite a bit of microseismic monitoring and other kinds of science. And then when they think they have it figured out, they stop. And they may come back and do a check the next year, or just do one or two, just to see, does it still look like it's working out? But once they get into development, they think they understand it, there's really not a lot of need for doing more of it. It's really meant to be there to help us understand, okay, how do we optimize this? How do we really figure out how to get the oil and the gas out?
Please grade the industry as a whole in terms of overall efficiency of getting the product out of the ground, i.e., what is industry's grade for, quote, effective fracturing, unquote?
Well, that's a tough one. From my perspective, I don't think it's very good, and that I think we leave a lot of resources behind. And the reason is because, right, industry's out there to make money. Obviously they do it by extracting gas, and getting more gas out gives them more money, but they have to get gas out at some reasonably fast rate so they can get the return on their investment in some reasonable kind of time period. Sometimes that doesn't necessarily square with getting all the gas out. So you think of a national oil company, for instance, like you'd have, Petrobras or PDVSA or the oil companies, Aramco and all those. They don't care so much about making money, they care about their resource because they own that resource forever. The companies that are actually doing this now, they may own that resource for 10 years and they may sell it then. Once the thing starts depleting a little bit and the pressure goes down, they may actually sell that resource to someone else. And then someone else is going to be working on, okay, how do I get more gas out of this? Do I have to refrac it? Do I have to drill more wells and do other things? So if there is this issue of how do I make sure it's economic, I make enough money, but still get as much gas as I possibly can, because that's the whole objective, obviously, is to do that. And there's a lot of trade-offs there. So if you ask, do we do it the most efficient way possible to make sure we extract all the gas? The answer is, I'm sure we don't. But could we do it and be economic if we try to extract all the gas? The answer is probably no. So there's always going to be some trade-offs there, and they probably do it about as efficiently as you can. I'm not sure I could tell them how to do it any better.
As you stated, the science is complicated and can be difficult to understand. So how do you engage with someone who is more comfortable basing their opinions on their fear and inability to understand the science?
Yeah, well, that's a hard one. But there's two classes of people like that, right? There's some that don't want to listen, that they have their minds made up anyway, and there's no point in talking to them. And there's others who, okay, convince me. And they're, because it is a complicated thing with complicated geologies, all we can do is just provide the data and the evidence that we have. And whether that's enough to convince them, that's hard to say. But that's what we try to do with data like I showed here. Is this is what we know. It's the science. Whether you want to believe that or not, okay, I can't convince you. Tell you exactly what that means and what is the risk and what are the hazards. It's very difficult to do that, but this is what the data is, and this is what it leads us to conclude, and you can take that for what it's worth.
I have two questions of my own, one of which is, that was very striking to see how many studies and how much transformation there's been of the tiny group of you before and now all of these people studying it. Are you in any danger of overconfidence because you have that greater body of knowledge? And I say that in light of what you said about all the variation in local geological structure. Is there any risk of thinking, well, we know a lot? I don't ever get to have that feeling myself, so I just wonder, are you in any sense of just wanting to take precautions against thinking, now we got it?
I think it's well worth taking precautions on things like what's happening at the surface, because I really think that the surface is where there's the potential for lots of problems. But I assume you're talking primarily about the downhole, the reservoirs, and what happens. My feeling is if we're working below 4,000 or 5,000 feet, which is where most of these shale reservoirs are, I honestly wouldn't even worry about it. I think knowing what I know about the way fractures work, the earth works, the stresses, sedimentary basins, all the layers, all the geology, how that actually retards fracture growth vertically, my feeling would be that there's very little to worry about. Where you need to start thinking about it is that as you get shallower and shallower and shallower. So if someone's working on reservoirs in Montana, for instance, there's some reservoirs at 700 feet. Well, you need to be very careful. If you're working at 700 feet, to make sure that you understand what's there, where the aquifers are, where your zone is that you're going to fracture, where the gas is, what you're doing, how you're completing it, what you're putting into it. There's a lot more issues with the shallow situations. And I think people do that. I think when you get to these shallower environments, there is a lot of a lot of emphasis by the companies. And I can't say every company. There's always some company that's going to take a shortcut, I guess. But most of the companies really pay a lot of attention to this and go through all these details to make sure that they're doing this right and they're not going to get in trouble and they're not going to have problems with the state and with the landowners and everyone else. So that's probably where the main issue is.
And then the last question about your social life, which is whether you end up in, no, there's going to be a rhyme and reason in this, just hold on here. So,
Okay.
do you end up in social circumstances, and if you were to end up at a dinner party or dinner gathering, and one of the Patricia Nelson Limerick hopes for a better society is that no one will have a dinner party without inviting an engineer so that the conversation gets better between people in line of work. So, okay, so if that takes hold, and if you were in a social event where there are a good festive group and it's going well, but there is, say, one person there who's a Western historian who thinks that she or he knows too much about mining and other forms of excavation and transformation of the land, so that person knows about the Butte Berkeley pit, that person knows about the Bisbee. I mean, they know about stuff that people have done to the earth in American West. And then another person is a good soul, a dear soul, a gardener, somebody who just feels we should be treating the earth with respect. And when we go far beneath the surface and do things that we can't see, that there's something just morally disturbing about taking that stance. So if you're in that social situation, and it has been a delicious dinner, let's just put that in here, it's been a really, an evening you wouldn't have wanted to miss, but those two conversational companions are there. One just really worried about that kind of violent treatment of the earth, and the other just worried about the historical record of sites left behind after a resource production. Do you look at your watch and say, well, I'm up early tomorrow morning and get out of there, or what would you do in those conversational circumstances?
Well, I guess if they want to talk to me about it, which sometimes they don't, but if they wanted to.
They invited you, so.
I guess my first comment would be, well, I like the earth as well, but let me tell you why I do what I do. And what I do, and all the rest of the people who work in the oil companies, is we provide cheap energy. And why do we provide cheap energy? What has it done for us? Well, it's the reason why our kids are going to college and not working in the fields. It's the reason why we all have cars. It's the reason why we all have how many TVs in our houses, and every kid has a smartphone and a Wii and a Game Boy. And the reason why we have appliances, and the women aren't stuck in the house anymore washing clothes by hand. They can all have careers. And the reason why we all live to be 70 or 80 years old, because we're out there developing all these new chemicals and labor-saving devices and things like that. And the reason why our lifestyle is what it is because of cheap energy. And if you don't want cheap energy, if you want something else where we're going to go back and we're all going to live on farms and develop that, that's fine for you, but that's not, I don't think, what most people want. I think most people would like to keep their lifestyle as much as possible without harming the environment, for certain, but keep their lifestyles, and that's what I try to do.
Okay, thank you for taking on that.